to ice.
Oh, God, that is intense.
His fascination is leading him farther and deeper into the cryosphere, the frozen regions of the Earth.
I feel like I'm not on planet Earth right now, like I'm in truly some extraterrestrial environment. The world isn't supposed to look like this.
What began as a photographic assignment has become a mind-blowing odyssey into an unpredictable world, where entire landscapes teeter between solid and liquid states. On the Greenland ice sheet, a crack opens, and a mile-wide lake pours down a 3,000-foot chasm.
But this water is just drilling down into the ice sheet.
One of the world's biggest glaciers shears off an iceberg that is nearly 1,000 feet thick.
You're not supposed to be able to witness things like this. Human beings don't generally get to see these massive features of the landscape changing and vanishing in front of your eyes.
Changes in the ice are normal. It is volatile and constantly in flux. But what Balog is witnessing suggests something extraordinary is going on. His passion is to document it and help scientists understand these monumental changes.
Many of the changes we're seeing are unfolding faster than our ability to really understand them.
Our relationship with ice is one that has very dramatically, if not violently, shifted from one of, don't worry about it, to one of, boy, you know, this is one of the most important controllers of the future environment of the planet.
Balog's work frames one of the most important scientific questions humans have ever faced. How fast will the world's glaciers and ice sheets melt? And what will all that melting mean for us? As scientists try to figure it out, Balog is finding evidence to help answer some of these questions.
Got it.
His Extreme Ice Survey is the largest photographic study of the cryosphere ever attempted. He is deploying 26 time-lapse cameras on glaciers across the northern hemisphere and programming them to shoot a frame every daylight hour for 3 years. It is a massive challenge in some of the most hostile regions on Earth.
So everything we're trying is getting thwarted. Trying not to be frustrated.
But the pain is starting to pay off, with thousands of frames revealing unparalleled changes in the ice.
My hope is that it will be powerful and immediate enough that people will say, yeah, I get it, I understand it. Okay, this is real. This is forensic evidence of the reality of what's happening.
The fact that the ice is changing is nothing new. Over the millennia, the expansion and contraction of ice across the continents has fundamentally altered the planet, gouging out lakes and valleys and pushing man around the Earth.
The waxing and waning of the ice sheets have been implicated in who lives where and what they do, and there are even some people have suggested that we're humans now, in part because we were responding to the changes in our environment that were linked to the growth and shrinkage of the ice.
In the past, the cycle of ice ages and periods of warming were caused mainly by shifts in the Earth's orbit around the sun. But now, humans seem to be driving these changes. Since the Industrial Revolution, our burning of fossil fuels has ratcheted up the output of greenhouse gases, like carbon dioxide, which trap heat in the atmosphere. Temperatures are climbing, and the ice is melting faster than ever.
I think that if we stay on the path we're on, we will change the amount of land ice, and therefore we will change sea level. The real questions, the more complicated ones, are how fast are we going to get there? How much is it going to rise? Can we put the brakes on it at any point?
It is the speed of the melt that is most astonishing. And nowhere is it happening faster than in the glaciers along the west coast of Alaska. Glaciers are like massive ice factories. High in the mountains, snowfall builds up and is compacted over hundreds of years. Gravity pulls it down in colossal rivers of ice. Some glaciers flow all the way to the ocean, shearing off icebergs in a process called calving. Over the last 40 years, temperatures here in Alaska have risen about 4 degrees Fahrenheit, twice as fast as the global average. Now, these rivers of ice are flowing faster and crashing even more spectacularly into the sea. Some people are taking advantage of the glacial fireworks while they last. Surfers towed in by jet skis are playing a dangerous game of chicken with the ice. It is rapidly calving glaciers like these that are the main contributors to rising sea levels. Alaska's Columbia is one of the biggest ocean-feeding glaciers in North America. In the early 1980s, the Columbia started flowing faster and began calving far more ice into the ocean than was being replenished by snowfall upstream. Baylog and the Extreme Ice Survey glaciologists are trying to figure out how much ice the Columbia is losing and whether or not it can survive. In the shallow waters of Columbia Bay, melting icebergs jam up before being carried away with the tide. This is the end of the line for the Columbia, a crystal maze of deteriorating ice that draws Baylog in.
Out here. Basically, we're looking at a whole landscape full of crystals. It's a cool spot. There's a lot of power here. It seems to be calm, it seems to be still, but there's this constant energy of the sea coming and going and carrying this huge glacier away. Every time you go in here, you're taking a risk because these bergs are inherently unstable. But you get seduced by the beauty of it, you know, you just get drawn in. It's like the sirens of Columbia Bay pulling you in, luring you in, going, come to me, come to me, come to me, and you just keep following these beautiful objects back through the labyrinth. But okay, Jeff, right about on this line here. The light that really makes these sculptures come alive is bouncing off the surface of the water. So the bergs are lit from within. Oh.
At the Extreme Ice Survey camp, glaciologist Tad Pfeffer tracks the flow of the Columbia. As the glacier moves, it churns up dirt and rocks that collect on its surface. The Columbia is so vast, it's hard to imagine it vanishing. Pfeffer and his colleague Shad O'Neill are taking its vital signs, measuring the speed of the glacier over several years to determine whether it's speeding up or slowing down. To do this, they fire a laser survey gun at reflective targets that they must deploy on the surface of the ice. As the pilot hovers a few inches above the glacier, O'Neill positions the target onto the ice. Pfeffer locks on to the target and shoots a laser that reflects back to the stationary gun, recording the position.
I got it, you're good. Come on back. Okay, first one down. 1.1 kilometers away.
The target moves with the ice. By tracking its movement with a laser over several days, they will be able to calculate the speed of the Columbia. Just down the fjord, Baylog and Extreme Ice Survey engineer Adam LeWinter climbed down to one of the time-lapse cameras they installed a year ago.
Oh, yes, here it is.
Still all there?
Yeah, the camera's here, but
Nice.
what happened to the glacier? When I was here a year ago, the calving face was just right there. All right, we have pictures.
The time-lapse brings to life the dynamic nature of the glacier, the ebb and flow of the ice as it calves.
It's a revelation. Every time we open up these boxes and download these images and bring them up on the computer and play them back, your eyes are popping out of your head.
Although calving is normal, the Columbia is hemorrhaging ice so quickly that in the last 30 years, the glacier has receded 10 miles up the fjord. Baylog's time-lapse images capture a rate of retreat that shows no sign of stopping. In the last year alone, the Columbia lost another half-mile of ice.
I really never expected that we were going to see changes of anything like this kind of magnitude in the period of time we had to work on this.
This rapid calving of the Columbia is a symptom of its decline, but it's poorly understood. If Pfeffer and O'Neill can figure out what's causing it to calve more ice, it may help them predict the glacier's future. They're taking a curious tack by using earthquake technology to crack open the mystery of the ice. They are installing seismometers that pick up the vibrations of ice quakes, tremors that reverberate through the ice as it calves. From the seismic data, a pattern emerges that points to one clear culprit: water. They knew water was melting the ice, but it appears that it's prying the ice apart like a powerful lever.
You can hear meltwater running right now, and it's all getting stuck in the glacier. And if you have a fracture with high pressure water in it, it can ratchet the crack open.
The seismic record confirms that the calving events have the unique signatures of fractures caused by water. As rising temperatures create more surface melt, the water pours into the cracks in the glacier and wedges it apart. The result is increased calving and a quicker demise of the glacier.
Oh, there's a big one coming up from underneath. There it is.
Baylog is seeing this powerful fracturing effect firsthand as the fjord below comes alive.
That basal ice has come up from the very bottom of the glacier, that dark blue out there. As the ice and the snow are squeezed together, the air gets driven out of it. And so the color becomes more and more pure. The air bubbles are what make it white. And so when the base of the glacier breaks up, you get these fantastic sapphires and turquoises boiling up out of nowhere, you know, and that's what these bergs are.
Meanwhile, after several days of laser tracking, Tad Pfeffer knows how fast the Columbia is moving. 50 feet per day, 8 times faster than it was 30 years ago.
Go back to 1980. Here, on this bedrock, we had ice above us 1,500 feet. Look at the trim line over there. That's where the ice surface was in 1980. And all of that volume is lost because this calving is so fast and snowfall upstream isn't resupplying it. So in that sense, yeah, it's going too fast and the glacier is kind of collapsing.
Pfeffer suspects that the Columbia is long past its tipping point, and it's only a matter of time before it withers away entirely.
This kind of ice is called dead ice. It's no longer part of the living, active glacier. It's stranded up on the side of the ice stream, and it's melting away and collapsing. And as it does that, all the erosional debris that's on the top continues to concentrate until you have this ice covered in blackness.
I'm really interested in the mortality of the glacier right here. There's something very rich and very intense about the changing landscape. You know, I feel the end. I feel the death right here.
The problem is, it's not just the Columbia that's on its way out. Glaciers everywhere, across the Rockies, Andes, Alps, and Himalayas, are in their death throes.
The people that live near the mountains and watch the glaciers know that the world is changing. We are heading towards Glacier National Park without any glaciers. We're seeing, huge changes in Glacier Bay in Alaska and other places. If you go, if you look, you see it.
The consensus is that in the next 50 to 100 years, mountain glaciers almost everywhere will simply disappear. From the loss of mountain glaciers alone, sea levels will rise by almost a foot, displacing millions of people around the world. But the biggest cost will be the loss of these huge natural reservoirs of fresh water, water that 1/6 of the world's population depends on. The hardest hit will be in Asia, where nearly 1 billion people get their drinking water from Himalayan glaciers. The abrupt collapse of the world's mountain glaciers raises even more disturbing questions about the Earth's biggest tracts of ice: the polar ice sheets of Antarctica and Greenland.
The real wild cards are what the big ice sheets are going to do. We're already seeing the Greenland ice sheet start to behave in rather disturbing ways.
We're playing with fire, if you will, when it comes to the ice sheets. We don't know whether if we get these big, massive, freight train-like beasts going, whether we can stop them.
The potential for the polar ice sheets to flood the planet is staggering. If all of Greenland and Antarctica were to melt, the oceans would rise 200 feet. But over geologic time, these ancient bulwarks of ice have withstood many bouts with climate warming. Until a few years ago, scientists thought the ice sheets were simply too big and too dense to be an immediate risk. But the latest evidence is making them rethink. The first wake-up call came from the West Antarctic Peninsula. In the summer of 2002, a NASA satellite photographed a Rhode Island-sized slab of ice called Larsen B as it sheared off the ice shelf. Other collapses followed, turning the assumption that it would take thousands of years for the big ice sheets to melt on its head.
The ice sheets surprised us. We sort of thought that the little glaciers would melt when it got warmer and that the big ice sheets wouldn't do much. And all of a sudden, the big ice sheets started rumbling faster and the Larsen B was falling apart. And we said, whoa, that wasn't supposed to happen.
On the other side of the globe, Greenland's cache of ice is also showing signs that it's starting to feel the heat. In the last decade, temperatures here have shot up by about 5 degrees Fahrenheit. NASA satellites are already detecting a meltdown around the edges of the ice sheet. Global warming is hitting hardest in the Arctic, and all eyes are now fixed on Greenland's ice. Its next move could be the game changer for rising sea levels. In the heart of Greenland, Beilage and scientists encounter an entirely different realm. A single slab of ice about 1,500 miles long and 500 miles wide. It's mid-July, and the summer melt on the Greenland ice sheet is in full swing.
It's sort of like an ice version of Kansas out here. It feels like you're out in the Great Plains and it just happens to be white and there's this vast dome in the sky overhead. It's unbelievable. There's no sound at all. No sound except the wind and the water. It looks quite featureless when you just look horizontally. But as you walk over it and you look down on it, there's a tremendous amount of texture and detail in here. This entire surface is like one gigantic Swiss cheese.
During the melt season, the sun's heat transforms the surface of the ice, creating a landscape that constantly shifts between solid, liquid, and vapor. The meltwater courses through the ice sheet, searching for a path down. Figuring out how this complex plumbing works is essential for predicting the future of the ice sheet.
Oh, man. Look at that. Whoa, that is intense. Oh my God. I can see, I think, maybe 250 feet down into the dark. No sign of the bottom. But this water is just drilling down into the ice sheet. There's this great unknown here, this great mystery of where does all this water go and what does it do to the flowing and the melting of the ice sheeting, sending it out to sea? Nobody really knows.
Beilage wants to get a shot that delves deep into the underbelly of the ice. The only way to secure his ropes is to thread them through the ice sheet.
You know, this ice sheet is cooking down and melting a lot, so this whole top 1.5 feet where you would normally put an ice screw is rotten and loose. Whereas here we're actually using the ice sheet itself and the strength of the ice to anchor the ropes. So here we go.
All right, a little slack.
Okay.
Wow.
Yay. How about that?
These giant holes, called moulins, are thought to bore thousands of feet through the ice to the bedrock. But nobody has ever been down there to find out.
Oh, God. That's the first time I've really seen the hole down there. Dave, this whole balcony could go any second. Here it goes. It's a strange, evil, gorgeous, horrible, fantastic place. Wow, I mean, there's hundreds of years of ice here layered in, and we're looking into the cross-section of this life history of the glacier. And it's so beautiful, this insane aquamarine and all this scalloping and fluting from the water. What a spot.
Beilage is just scratching below the surface of the ice sheet. Below him is another half-mile of solid ice. In these compressed layers of the ice sheet, there are clues to how fast Greenland could melt. At the National Ice Core Lab in Lakewood, Colorado, a giant freezer stores over 45,000 feet of ice, drilled from 34 sites around the cryosphere. Dating back hundreds of thousands of years, these ice cores are time capsules that allow scientists like Jim White to peer deep into the history of ice.
This piece of ice is interesting because it has a couple of things you can see right away. One is there are bubbles throughout here. These bubbles are little packets of air. It's these bubbles we can take out and measure CO2 and methane and nitrous oxide. It's the only medium that really collects the atmosphere itself. The other thing you can see in here quite clearly is you can see the layers. And the thickness is going to tell you how much snow fell that year. So you get a couple of pieces of climate information and a dating scale just out of visually looking at this ice core.
Most importantly, scientists have identified a direct historical link between increases in greenhouse gases like carbon dioxide and steep rises in global temperatures. At every peak, big rises in sea level followed as Greenland's ice sheet shrank. The ice core records also reveal a particularly telling moment in Greenland's history. Roughly 125,000 years ago, temperatures rose by about 7 degrees Fahrenheit. The entire southern portion of the ice sheet melted, and global sea levels rose by over 10 feet. It was caused by a change in the Earth's orbit around the Sun, which increased temperatures and released carbon dioxide from the oceans. The more recent ice core record shows the potential for a similar meltdown. Right now, greenhouse gas levels in the atmosphere are even higher than they were 125,000 years ago, higher than they've ever been in the last 500,000 years. Temperatures are already following suit. The only explanation is the burning of fossil fuels.
What we see in this ice core is very solid evidence that what's happening today in the atmosphere is different. It's not a normal part of the climate cycle. It's something caused by human beings.
Rising temperatures are once again pushing Greenland towards a major meltdown. But what the ice cores can't tell us is how long it will take. The last time Greenland lost a significant portion of its ice, White suspects it happened over thousands of years. But this time, it could happen much faster.
And here we are now, fiddling with the dials of the climate machine, not quite knowing what's going to happen. And we know from these past records that the climate system can come up and bite us hard.
So far, global warming is biting hardest at the fringes of Greenland's ice sheet. Ringing the island are hundreds of outlet glaciers that act like pipes, draining the interior ice sheet out to sea through narrow fjords. In the late 1990s, many of these spigots began gushing more ice. One of the largest, Jakobshavn, is now pumping out over 40 billion tons of icebergs each year, more than any other glacier in the northern hemisphere. These icebergs reach the open ocean at Disco Bay. In this deceptively peaceful icescape, James Baylog is on the hunt for giant bergs. Some of these blocks of ice rise over 300 feet above the waterline, but 90% of their mass is hidden below.
Oh my God, these things are gigantic. If they roll over, we'll be swimming with the fishes. But right in here, there's this line of jewels as you come around the arc of this berg, and all the water drops are coming in, and the sun makes this fantastic necklace of jewelry along the edge of this. Oh man, I can't. Let's do it again. There's something in there.
It's making me crazy, actually, because there's a picture in here. There's definitely a picture in here.
Wow, that was amazing.
"35 miles up the fjord from Disco Bay, Baylog's time-lapse cameras are stationed above the calving face to capture Jakobshaven's every move. Baylog has teamed up with glaciologist Jason Box, who has been keeping a close watch on Jakobshaven and other glaciers along the coast for the past 14 years.
The Jakobshaven Glacier is the king of glaciers in Greenland. It produces by far more icebergs and more ice flow than any other single glacier. This is really where the rubber hits the road in terms of sea level rise. Glaciers are, of course, very dynamic systems, but you don't really see that when you sit there and stare at them. We're able to observe with the time-lapse cameras at a much higher frequency, like every hour, whereas from satellite you can only observe the glacier every 10 days or so.
What they are finding is that the ice is far more sensitive to temperature changes than they thought. During the summer melt season, Jakobshaven is now moving at a clip of 130 feet per day, almost twice as fast as a decade ago. The faster it goes, the more pressure builds up behind the glacier's 400-foot-high calving face. This triggers more frequent and explosive calving events. In the spring of 2008, Baylog's team was staking out Jakobshaven and got lucky, capturing the largest calving event ever filmed. In the space of about an hour, a section of ice as wide as Manhattan sheared off the glacier.
We've underestimated the sensitivity of these systems. We are approaching the threshold of viability for the Greenland ice sheet, and that's when the melting occurs high enough on the ice sheet that no matter how much snow accumulates, there's net loss every year.
Greenland is already losing 150 billion tons more ice every year than it gains in snowfall. As temperatures go up in the coming decades, even more ice will be lost. The hard part is figuring out how much and how fast.
There's big questions now that we didn't think we were going to have to solve. They're hard questions. Ultimately, you crank up the temperature in the air and the ice sheet notices and it flows faster and it raises sea level. But how fast and how much are questions that really we don't have answers to.
Some of those answers may be hidden deep under the ice. The summer melt season on the Greenland ice sheet has grown hotter and is now 2 weeks longer than it was only a decade ago. Rivers of meltwater cut deep into the ice, creating a serpentine canyon that winds for miles.
This is one of the most exceptional landscapes I've ever seen in my life. You know, this looks so much like those incredible canyons out in the sandstone country in Utah. And you have that, except it's sculpted out of ice. It's like this huge, incredible cake sculpted by this river in here, and it's like the world isn't supposed to look like this.
As the summers heat up, features like this ice canyon are becoming more pronounced. But for all its beauty, it raises perplexing questions about the effect this water is having underneath the skin of the ice sheet. The strangest phenomenon is the mystery of the meltwater lakes. As the ice sheet cooks down, the meltwater collects in depressions in the ice, forming thousands of lakes, some over several miles wide and nearly 50 feet deep. From satellite images, scientists noticed that in midsummer, many of these lakes vanished overnight, leaving bright circles where the water once stood. Until recently, it was assumed that the water was absorbed and refrozen into the ice sheet. But Ian Jochen and Sarah Das have a hunch that the water could be having a deeper impact. These events are so unpredictable, nobody has ever observed them. But Das and Jochen just came close. A few days ago, a big lake by their camp suddenly drained out.
We were in the fog, so we couldn't see the whole lake. While standing right on the shore of the water, we started to hear some really loud booms and pops, and it was just extremely spooky. Cracks would run across the ground beneath your feet. It was all around you. It was a strange experience.
Frightening, but also fortuitous. They had placed a device that measures water pressure called a pressure logger in the bottom of the lake, hoping it might drain. If they can find the logger, their bet might pay off.
The fish line that we're following, it's tied at one end to our stations, and it's tied at the other end to an old plastic bottle that has a pressure logger attached to it, and that's sitting in the lake basin. And so we're following the line out, hoping that at the end we'll find it tied off to our loggers.
The loggers should reveal exactly when and how fast the lake drained. Everywhere, truck-sized blocks of ice litter the lake bed, evidence of the violent forces uncorked as the water rushed out.
I see
Hey,
it!
there it is.
Whoa.
In
there, under the ice.
Watch your fingers. I'm in.
There's one of them.
With the loggers in hand, they can now plot out the minute-by-minute account of the mass draining of the lake.
So what you see here on the left is early June when there's no water in the lake. And as more water fills the lake, the pressure goes up, the height of the water column goes up and up, up, continue to fill till about this point. And then on July 10th, boom, you see the lake drop in a matter of about 40 minutes.
GPS data reveals that so much water drained out so quickly, the surrounding ice was pushed up by several feet.
Well, as you can see from the blocks all around us, it's a tremendously violent event. You have a lake that's 2 miles wide, 40 feet deep, and all of a sudden it drops 3,000 feet through the ice. It would have basically been one of the tallest waterfalls in the world. The flow into these cracks in the lake bed is greater than the flow over Niagara Falls.
Instead of being absorbed and refrozen into the surface ice, they discovered that the water dropped all the way to the bedrock. There, it lifts and lubricates the ice sheet and accelerates its slide.
And if you have increased warming, especially in the summertime, over the ice sheet, you're going to just increase the supply of meltwater to the bed, and potentially that could escalate the speed up.
Their breakthrough solves the mystery of the meltwater lakes. They'd measured it, but because of the fog, they hadn't seen it happen. By sheer chance, the very next morning, Balog and the scientists would witness it firsthand. About a mile away from his camp, a smaller lake that was full only hours before suddenly starts to drain. Balog heads for the water line to try to find where the water is going.
This is the world's most treacherous footing. These wave cups are hard walking as it is, and with them just emerged out of the lake, they're slick as can be. There's so much water packed in there. It's just like grease on top of glass. Oh my God. Not being roped up here is one of the scariest, dumbest things I've done in my life. Where I'm laying right now was underwater just 6 hours ago. You know, there was a lake here, and the water depth of the lake was roughly 20 feet right here. And all of that that was overhead 6 hours ago is drained out and poured down this hole. And I can see maybe 250, 300 feet down there. I'm not feeling real comfortable out here.
This is really the first time that we've been able to observe these things firsthand actually happening. And it's really nice to see that our theories that we've pulled together from our instrumental records match our observations on the ground very nicely.
Now they know. These billions of gallons of water are finding a route under the ice and out to sea, lubricating the outlet glaciers and making them speed up. Das and Jachin calculate that this lubrication effect accounts for about 10% of the increase in speed. So there must be another powerful force behind the surge of ice from Greenland. The latest ocean research may have found it. Around 1997, there was an abrupt 3-degree Fahrenheit jump in coastal water temperatures, exactly when the outlet glaciers began to speed up. At the foot of Jakobshavn Glacier in Disco Bay, Ian Howitt is investigating how the warming ocean could be eating away at the edges of the ice sheet.
I'm trying to get a handle on how the ocean and the ice interact. And so by that I mean how heat is transferred from the ocean, which is this huge source of heat, up against this ice sheet.
To figure it out, Howitt is using a capsule packed with sensors that record temperature, salinity, and depth at intervals going down 1,000 feet to the ocean bed. The measurements give Howitt an immediate picture of how the meltwater streaming off the glacier and the denser salt water below stack up like a layer cake.
So this plot is showing the increase in temperature with depth. What we see here is very cold, nearly freezing water at the surface, and then as we go down, it increases its temperature as it mixes with the warmer ocean water below. So this transition zone, this almost flat line, shows us that there's a very sharp transition between that fresh water and the salty ocean water below.
Howitt thinks the rush of cold meltwater coming off the glacier might be creating a vacuum at the calving face that pulls the warm ocean water underneath it, delivering heat directly to the base of the glacier.
One hypothesis is that as you increase the melt and you increase the force of this conveyor belt of fresh water going out of the fjord, you're bringing more heat from the ocean into the fjord to melt more ice, and that would be a strong feedback that could actually lead to more glacier melting. It's a much more dynamic environment than we've thought in the past.
The story of the mountain glaciers and the ice sheets shows that abrupt changes in the ice aren't the exception. They are the rule.
There are concerns that we get to some point beyond which strong feedbacks in the climate system kick in and cause changes that we're really unprepared to deal with.
The ice may have more surprises to come, but based on the latest research, the best guess for future sea level rise comes down to a simple calculation. In the next 100 years, the oceans will expand on their own as they warm, accounting for about a foot of sea level rise. Another foot will likely come from the loss of the world's mountain glaciers as they melt away. The ice sheets of Greenland and Antarctica won't disappear, but their combined melt is expected to add about another foot. The total equals an estimated sea level rise approaching 3 feet or 1 meter by about 2100. It may not sound like much, but over 100 million people live within 3 feet of sea level. Cities around the world will spend trillions building up coastal defenses. Low-lying regions such as Florida, Vietnam, and Bangladesh will be devastated. Many island nations will cease to exist. The consequences will test our ability to adapt like never before. But it doesn't stop there.
If we look beyond 100 years, the biggest questions might even be what we do. There's huge things we don't know about the ice sheets, but our uncertainty about what we decide to do may be bigger than that. But if we make it really warm, I think a whole lot of us get really nervous about what the ice will do.
This is going to be one of the pivotal moments in human history. Ice is too important for us in terms of the climate of the planet, in terms of sea level, in terms of the fundamental operating systems of the planet, for us to continue to ignore it.
The final chapter of Beilag's story plays out on the southern coast of Iceland, where he discovers an unrivaled confrontation between the ice and the sea. "8,000 years ago, the island was encased in ice. But now the last remnant of its ice cap is quickly disappearing. As the ice seeps down towards the sea, it discharges into a meltwater lagoon. Each day, the tide draws the icebergs out into the North Atlantic.
I'm not aware of any other place in the world where you can see this dynamic between the ice and the surf in the same way.
What I see in this ice is a unique sculpture by nature. Each one is a hope diamond, you know, some really perfect, pure manifestation of form and color and texture. They come up here on the waves, they sit here for 12 hours after the tide goes out, then the tide comes back in, takes them away, and they're gone for good. And in that transitoriness, I see extinction. Our brains are programmed to think that geology is something that happened a long time ago or will happen a long time in the future. We don't think that that can happen during these little years that we each live on this planet. But the reality is that it does.
On On NOVA's Extreme Ice website, see dramatic graphics that show how the world's coastlines would change if all of Greenland's ice melted. Find it on pbs.org. ExxonMobil, taking on the world's toughest energy challenges. And by David H. Koch. And
discovering new knowledge. HHMI.
And by the Corporation for Public Broadcasting, and by contributions to your PBS station from viewers like you. Thank you.